all doing well and staying safe and healthy in this difficult time. It's my honor and pleasure to present this talk as part of the workshop on distributed cloud computing at ACM SIGMETRICS 2020. In this talk, I'll talk about how we can harness the computing continuum for urgent science. I will describe what I mean by computing continuum and urgent science, and then talk about some research activities as well as software tools at the Rutgers Discovery Informatics that my team and I have been working on to address this issue. This is work in collaboration with my co-authors, Danielle Baluch-Tomert and Yvonne Rodero. Here's a quick outline of my talk. As I mentioned, I'll provide some context talking about the data-driven workflows as well as urgent science. I will then talk about the computing landscape and define what I mean by computing in the continuum, and then I'll talk about how we can harness the computing continuum for urgent science and describe some of the activities that we have been doing to support this. And finally, I'll conclude the talk. We are in the era of big data and extreme compute. I'm sure I don't need to convince any one of you about this, right? There's an infographic there on the right of the slide, and I must apologize, it's already very outdated, but it tries to highlight the amount of data that's streaming towards us every day, every minute of every day. It includes data coming from many social media sites, data coming from sensors, Internet of Things, different applications. It's just a very, very large amount of data. All right, and we have to admit that data and computing are pervasive. What does that mean? It means that we have data everywhere and have access to data anytime, anywhere, as well as computing, non-trivial computing that's accessible to us through our mobile devices, to edge services, to cloud services. We're also talking about extreme scales, both of data and compute. Right, we're talking about exascale in 2021 and exabytes of storage. This is a lot of computing power that's accessible to us. There's some information example on the right side that gives an idea of what an exabyte of storage, amount of information that can be stored. But it's not just the accessibility or the scale of computing and data, it's also the disruptions that we are seeing in terms of novel paradigms, cloud services, serverless computing, Internet of Things, fog and edge computing, in-transit computing, software-defined networking, network function virtualization, a whole set of different paradigms that can add a lot of value as we try to imagine and build the next generation of applications that can impact every aspect of our life. Underlying a lot of these new paradigms are disruptive technologies, whether it's through AI and ML or through special purpose hardware and accelerators such as tensor processing units and neuromorphic chips and reconfigurable computing chips, new storage and communication devices. There's a lot of disruption that again can enable new capabilities, but also brings with it challenges. And finally, we have concerns that are becoming, that are highlighted now. I wouldn't call them new concerns, but concerns that are becoming increasingly important. And these are concerns around correctness, energy efficiency, fault tolerance, but also non-technical concerns such as fairness and privacy that we have to address. So if you put all these things together, we have emerging a computational ecosystem that connects all these pieces together. Right? It connects the data that's streaming in from experimental facility or observatories or sensor networks, along with large amounts of computing that's accessible to us. And it puts it all together to really close the loop where we can acquire the data, assimilate it, analyze it, feed it into predictive models, and then use the outcomes of this to actuate, to manage, optimize different aspects of our life, of our environment, in a closed loop fashion. Right? So there are emerging dynamic data-driven applications that are really following this pattern of closing the loop. Right? And these are driven by unprecedented instrumentation and the extraordinary growth of digital data sources. And they also involve large amounts of data that's processed by complex application workflows. And if we can do it in a timely manner, we can really do this closing of the loop that I illustrate in the graphic on the left. And there are many applications in almost every domain, whether you talk about precision medicine or smart infrastructure, buildings that can use models and sensing to be able to optimize their operation, to do things more economically or more optimally or in a more environmentally friendly manner. We can think about roads that sense traffic and sense weather conditions and are able to optimize our driving experiences. So one can think of applications in almost any discipline that can build off this model and leverage this emerging ecosystem that one thinks, right? A class of such application is what we call urgent science, right? What urgent science are scientific applications that are data-driven, that leverage distributed data sources and facilitate important decision-making in a timely manner, right? We can think about application that sends data that's coming in from sensors and are able to process that data and make adequate predictions that allows us to take corrective action or minimize damage or minimize impact of such events. Right? So if you look at the requirements of these applications, there are a few of those listed on the slide. For example, you need real-time data delivery, right? Or near real-time data delivery. Given that the data is distributed, we want to be able to get results to the user in time so that they can make the required actions or take the required actions in preventing, for example, the impact of an event, for example, right? Since the processing involves complex models, we want adequate computing capabilities that can do the processing and do this with sufficient accuracy so that the results are within the error thresholds, again, to make sure that I can drive decision making using this processing. Often these sensors or the instrumentation is far away from where the users and the computing is, and so we need adequate data transfer capabilities. I think most importantly, since a lot of the processing depends on the data, so what data I process, where I process depends on the content of the data, so I need flexible workflow abstractions as well as automated execution mechanisms that can automate this process in a purely objective-driven, data-driven manner, right? So that I can execute these workflows in a timely, automated way to have the most impact. To give you one example of such an urgent science use case, consider an early earthquake early warning system, right? So earthquake early warning systems are really systems that are put in place that get data from multiple sensors and try to notify the community about potential earthquakes so that the warnings can result in adequate actions being taken to minimize damage or to protect life or to take appropriate preventive actions within the community. Right? And what this involves is collecting the data and then processing that data to be able to characterize the magnitude, location, speed of displacement, etc., so that you can make as accurate as possible earthquake warnings. Right? And what happens here is a single data source is not able to cover the whole spectrum of events, right? So we have to use a combination of sensors to be able to do that. You need seismometers, which work well for smaller earthquakes. You have high precision GPS systems, which work better for larger earthquakes. And what the traditional way to do this is to take all the data and then collect it at a data center computing facility, and then make a decision and issue broadcasts from there to be able to warn the community. And so there's a trade-off here, right? Given the latencies in collecting the data and the time to process the data, you trade off between how much data you process and how soon you process it. If I waste too much time, I can process more data, improve the accuracy, but then I have less time to react and for the community to react, right? And vice versa, I can have more errors in my results, but then I do it quickly, and so that trade-off is hard to make, right? Also, there is a set of different waves that are tracked. There's a P wave that comes in early, that's harder to detect, but travels much faster than the S wave, which actually causes a lot of the shaking of the ground. But then, and that's easier to detect. But then you have less time to take actions if you rely on only the S wave. So how do I use a combination of P waves and S waves to be able to do adequate detection of the earthquake, right? So our goal here is to combine multiple data sources to cover the whole spectrum of events and leverage the computing continuum for timely processing. A big part of that is to come up with an algorithm that doesn't only rely on the centralized computing capabilities, but can use the continuum to do that. There's a citation there which really provides details about the formulation and the algorithms that we built to support this. But let me switch a little bit and define what I mean by the computing continuum. So if you look at the computing landscape, we can think about a very heterogeneous and geographically distributed landscape. You have a lot of resources at data centers, at clouds that are large scale, are very reliable, relatively inexpensive, and can be seemingly infinite, at least from an applications perspective, right? The problem is that they tend to be far away in terms of latency from where the data is and where the users are. And so data access and data transport can quickly become expensive. We're also seeing the emergence of fog and edge computing, which are resources that are placed closer to the edges of the network, closer to the data sources, which can then reduce the latency significantly. However, they tend to be limited in capacity, also tend to be a little more expensive than your cloud resources, and there is increasingly you have increasing access to in-transit computing that are resources that are distributed along the data path, which can be used sometimes opportunistically to be able to process the data as it's transported from the source to the destination, right? So these are different types of computing which provide different capacities, provide different latencies, right? And they're typically being used either or, right? You do a lot of things on the edge using edge devices and edge frameworks, and you use a lot of things where you transfer the data at the core, right? And so the idea behind continuum computing is to how to use them collectively. Can I leverage all these devices together so that I can use and process the data in as effectively as possible to meet the objectives of my application? Can I leverage the resources at the logical extremes in the core along the data path to be able to address the needs of my application workflow and have the right trade-offs between latency and compute capacity, right? And so that's the basic idea behind computing continuum, using these resources together to be able to achieve my goals, sometimes in an ad hoc and opportunistic manner. There are a bunch of, if I try to really implement continuum computing, there are a bunch of research challenges that I need to address, right? So since a lot of the aggregation and deciding when to compute and what to compute depends a lot on the data that I'm trying to process. So how do I drive the computations to data? How do I express application behavior based on the availability of data and its content, right? So what I'm trying to do depends on what data exists and what does the data say, and that might define what workflows run, where they run, how often do they run, how fast do they run, how much am I willing to pay for those workflows. How to accommodate uncertainties in data and computation. All right, so since there's a natural uncertainty both in terms of the data, the quality and availability of data, as well as the resources that exist along the data path and in the continuum, and how do I move away from precise definitions to approximations where I can start trading off latency, compute cost versus solution accuracy in a more dynamic way. And then how do I build workflows that encapsulate something so that they can adapt to increase value? For example, if I discover a new data source and that data source adds value to my objective, right, improves accuracy, for example, can I simulate it? Or a new resource comes in that allows me to better meet my objectives, can I simulate it, right? And so how do I build workflows that are able to do that in a dynamic manner? And I optimize the execution of these workflows as I discover and aggregate new resources along the data path. Right? So there are a lot of dynamic data-driven behavior here that I need to be able to program and then execute at runtime. And then how do I incorporate things like market models and trust models and utility into the entire ecosystem? This is clearly not a complete list of research challenges, but just gives you a flavor of the type of things one has to think about when tries to build this raw, highly dynamic and opportunistic computing environment by aggregating these resources and processing data as and when possible to be able to meet the application's goals. A big concept underlying this is one of autonomic management, right? And this idea is, how do I build systems that can use policies to orchestrate mechanisms in a dynamic manner? I can use them to optimize my resource provisioning as I define and I discover resources, or I come up with new application objectives. I can create models that translate these resource capabilities and availabilities into application utilities that allows me to define whether I'm willing to pay for another resource or am I willing to assimilate another resource as it becomes available to me. Does it really add value to my objective? And if it does, I'm willing to pay for it or pay in terms of cost or in terms of latency to assimilate. And same is true for data. I might discover a new data source, but if it doesn't add value, I don't need to pay for it. So how do I make sure that I can translate these capabilities into utilities at the application level? Similarly, how can I quantify errors and uncertainties that I encounter in my execution environment into confidence levels as a result? Right? So how do I try to see that by reducing cost or reducing latency or reducing the amount of computation, how does that impact my overall result? And again, the idea here is to be able to translate user-defined objectives into decisions that I can make at a system level as I orchestrate the execution of my workflow across the continuum. So how do I use this? How do I really leverage this continuum? So we've been trying to address this, and we have been building a framework to allow us to do that. And at a high level, the framework is divided into really 4 layers. We have an infrastructure layer that really consists of the different capabilities that are accessible, and these can dynamically change. A federation layer then that assimilates the relevant capacities that meet my objectives, my constraints. For example, I might require certain levels of performance or cost or security before I can use them. A streaming layer that then runs my data-driven workflows on top of this federation so that I'm able to compute at the right location on the right data point. And then finally a services layer that allows me to then build on these lower layers to realize my applications and to be able to do my end-to-end workflows. We have built services to really realize this framework, and this is encapsulated in three different components that are listed on the right side. I'm not going to go into details because I see that I'm running out of time. And so just at a high level, we have Comet Cloud that does really builds software-defined systems based on user constraints and resource availability. rPulsar is a framework that allows me to do a data-driven workflows. It's an edge-based middleware that has the abstraction that allows me to define on which data I process, where I process it, and when I process it. And then the Virtual Data Collaboratory is a way of being able to use shared data as a way to build workflows, data-driven workflows. There are some URLs here where you can find more information about these services. So quickly, in the few minutes I have, how do I leverage this continuum to do the earthquake early warning urgent science, right? So there are three steps here at a higher level. At the first step, I want to be able to manage what data I'm processing at the edge sensors. These are the seismometers and GPS sensors, which are generating 3D data streams, right? And these are thousands of sensors that we are processing data. So we can use rPulsar to program what data is interesting and where it gets processed, right? So we can use the rPulsar abstractions and middleware that runs at the edge that quickly defines what data gets processed, what data, where it gets processed and when it gets processed. And so you're doing some initial triaging of the data at the edge itself, right? Once we make that determination, we need to do local processing and regional processing of the data. And this is the classification step. We use, again, a combination of rPulsar and Comet Cloud to be able to provision data transfer nodes or DTNs in transit and then run the appropriate classification steps on local and regional data in the network in transit itself, right? And finally, we want to aggregate the results of this in-transit computation and do the final processing at the core and issue broadcasts, right? And so this is done by taking and transmitting these intermediate data in an incremental fashion to the core using appropriate windowing protocols. And here we use a combination of VDC, rPulsar, and Comet Cloud, each bringing capabilities. rPulsar allows us to really program these behaviors. Comet Cloud maintains the federation of both the core resources and the edge resources as well in-transit resources. And VDC provides the key stream processing services to collect and execute this data. We've prototyped this implementation. We're now currently doing an evaluation of this and trying to see how combining these resources gives us the required urgency in executing this workflow. And we are, at this point, generating experimental results based on actual data that we have from these sensors. To summarize, we talked about how we can enable urgent science. This is data-driven science that has to be done in a timely manner to be able to make critical decisions. It's enabled by large amounts of geographically distributed data as well as pervasive computing capabilities. Often, because the data is large and has to be processed centrally, meeting these time constraints without trading off accuracy becomes hard. So we are exploring how we can leverage the continuum. These are resources at the edges in the network and along at the core and along the data path to be able to use collectively and opportunistically to be able to meet the needs of these urgent workflows. And then clearly, as we have been doing this, we are identifying many challenges, and I listed a few of them. I want to thank you for your attention. Once again, thank you for this opportunity to present the talk, and I'll be happy to respond to any questions. My email and URL is on the slide. Thanks again.